Okay, same thing, part 2. So if somebody who switched on the light could be so kind to switch it on back, it was very nice. I'm afraid if I start pressing buttons, then okay, thank you. Okay, this will be a shorter one, I hope, but it never is. Let me start off with more definitions. So, classifications of chemistry. I will classify myself. I'm a physical chemist. Pitiful attempt to apply y equals mx plus b to everything in the universe. Organic chemist. My apologies. As I found out, Dave is the only organic chemist here. The practice of transmuting wild substances into I left out many publications, my apologies. Inorganic, that which is left over after the organic, physical, and analytical chemists get through picking over the periodic table. So, many universities don't have inorganic chemistry division. But my engineering colleagues really love me for this. The practice of doing for a profit what an organic chemist does for fun. All they care about is making money. That's all they care about, although they vehemently deny that. Okay, so I'll tell you, this story is about this particular beetle. Right? So this has connections now to liquid crystallinity. And I'm particularly excited about these beetles. It was about 102 years ago, Michelson, in fact, studied this, and he was very interested. So there's a very nice book on optics by Michelson, published in 1911. It's a Dover publication. And Michelson basically spent a lot of time looking at jewel beetles. And he studied, so he was very intrigued by the fact that these are incredibly metallic in nature. He also pointed out that even for someone who is very well trained in metallic reflectances, they would be hard-pressed to differentiate this particular beetle from a metallic substrate that reflects green. Right? So these beetles are, in fact, incredibly metallic in nature. And he spent a lot of time looking at the circular dichroism of these materials, and came to the conclusion, without knowing the field of liquid crystals, came to the conclusion that this circular polarization reflection must be because of some ultramicroscopic screw that causes this reflection. And much later, entomologists here, I think in Cambridge, either in Cambridge or Oxford now, I don't remember their affiliation, Neville and Cavenet studied these beetles, and they were the very first ones to make the link to the field of liquid crystals, and pointed out that the exocuticle of this particular beetle has all the optics connection to that of cholesteric fluids, and they of course had read. It's very rare to see entomologists reading liquid crystal physics literature, right? So, and they had looked at Bouligand's work and basically connected. They call these things Bouligand structures. So the paper by David Goldstein is a really beautiful paper in applied optics that has a whole host of historical stuff on beetles, if you're so interested. And David also, of course, made measurements of not just one, several jewel beetles. Now, these things are called jewel beetles because they were used in jewelry, as I said, and they still get used in jewelry. So this is a very nice paper as well by Michelson, and then there's Bouligand's paper. Now, those of you who listened to Linda Hurst's talk yesterday, and those of you who listened to David Walba's talk on chirality, would have noticed that the reflectance from cholesteric faces is almost always less than 50%. So if I have a left-handed helix, then the fluid phase reflects that handedness to 100%. So by that I mean you can consider unpolarized light to be a mixture of two circularly polarized lights, 50% left and 50% right, if you will. And so if it's a left-handed helix, it reflects all of the left-handed light. So you can't get more than 50% at best. So here's a beetle that reflects circularly polarized light, and in fact is able to get 100% of the light out. Now, the way it does it is actually quite beautiful. So these are electron micrographs after Cavenet in 1971. And so this is the left-handed helix, and then there's a half-wave plate. All the half-wave plate does is rotate the plane of polarization of the light. And then here's another left-handed helix. So this particular beetle gets 100% of the light out. This is also the beetle that Michelson looked at. This is also one of the beetles that he looked at. And so the left circularly polarized light is reflected off the top. Most of it is reflected. And the right circular polarization goes right through, goes through this half-wave plate. This is just an oriented layer of chitin with enough thickness so that it introduces a phase difference of lambda over 2, and you get the polarization to be rotated, and then the right circular polarization now is left circularly polarized, gets reflected from this and comes out through the half-wave plate, where the polarization rotates again and comes right through that. So you get 50% from the top and 50% from the bottom. So all of it is reflected back. But the interesting aspect of this is the entomologists are extremely clever. And so if you read the papers of Neville and Cavenet in 68, 69, and 71, these are absolutely beautiful. So what they did, they raised this beetle in the dark, and they raised the beetle in light. So if you raise the beetle in the dark, you get only the half-wave plate. You get only the oriented layers. There is no other helix. So it's basically chitin that is being deposited in a helical form when there is light, and chitin is deposited without a helix when there is no light. So in fact, the entomologist essentially can measure the age of a beetle by taking a cross-section of the exocuticle and figuring out how many half-wave plates is there in the exocuticle of the beetle. So this is in fact quite remarkable. So then David Walba was asking me, well, how does it do that? I don't exactly know, but here is a partial answer from Cavenet's paper. So if you look at only the cholesteric part, or the helical part of it, there is less uric acid if you do the analysis. And in this particular case here in the half-wave plate, you have an excessive uric acid. So the question then is, does the beetle somehow, light activated, secrete uric acid that unwinds the cholesteric helix? Well, at least that's the suggestion I have made in the literature, but that doesn't mean that's right. And so this image is taken from Meethouse paper in Advanced Materials in 2012. So as I said, you can buy these things. These were all used in jewels in many places, including India. So the question Mark Warner was asking me at lunch today was, well, do these guys sense circular polarization? So you can ask these beetles, but they don't talk back to you. However, what you can do is you can do behavioral studies. So that's what Brady and Cummings did, although this is a little bit controversial. There is another paper just 6 months ago saying there is no selectivity to anything. But the essential idea here is they essentially had food for the beetles, and one of the food piles was irradiated with left circular polarized light, and the other one was with right circular polarizers. And they asked how often does the beetle go to the left as opposed to the right. and their evidence seemed to suggest that the Chrysina gloriosa beetle responds differentially to left circularly polarized light. So the idea is the exocuticle reflects left circular polarization, and it has the ability to detect left circular polarization. I don't know if that's true. We have been wanting to sort of look at the visual system of these beetles, which we have not done. I'm sort of one of these guys who doesn't like to dissect anything. And if you don't dissect them, you can't look at the eyes very well. Okay, so this is a fairly short story, and so this is what we tried to do. So here is my beetle. Here's what it looks like under a microscope. It is quite remarkable. There are probably only 4 or 5, maybe 6 people on the planet who have done this, or at least reportedly anyway. So one of the groups is Pete Bukusic, Sharon Jewell, and Nick Roberts in Exeter. So they looked at these beetles as well, and we did under the microscope. And then there was this guy Anderson Pace from GE in 1972 who looked at these things, and almost nobody else has. It's quite remarkable. So if you were to look at this under a microscope, what you will find is there are all these very nice hexagonal and pentagonal and heptagonal cells. And the cells are, of course, there is a central yellow reflection, and there's a surrounding is green, and there are sort of grain boundaries, as it were. So we were quite interested in figuring out where do these patterns come from. So that's sort of the message in this publication. And it turns out that these beetles are also intrinsically fluorescent, so you can do confocal microscopy on them without actually having to fluorescently tag them. So this is what the confocal micrograph looks like, and it's far more clear here to see that there are hexagonal, pentagonal, and heptagonal cells. So I don't really want to spend a whole lot of time on any applications. The only thing that I want to provide you is that these exocuticles provide the structural colors, usually very metallic and iridescent. And there are people who are trying to make use of this to create devices. And one of those guys is Ian Hodgkinson in New Zealand, who has been studying these beetles as well. So what we wanted to do was ask the question, how ordered are these patterns on the beetle exocuticle? Right? So if I were to look at the beetle exocuticle, that you find all these patterns. And so we were quite interested in figuring out a couple of things. How ordered are these patterns, and what is the origin of these patterns? So these were sort of 2 things we were interested in answering, and hopefully I will answer them. So you can very easily convert such polygonal things into a Voronoi polygon. So you can ask, if I have this is in fact the breadth figures that I talked about. These are water droplets that are packed. So I can ask, how ordered are these things? If I pick one, it's hexagonal, and then I can go to the next one and the next one and so on and so forth. I can ask, how hexagonally ordered is this object? And this is something that David Nelson and Michael Rubenstein introduced. You can ask the question, what is the entropy in the system or the disorder in the system, by counting the probability that you will have n-sided polygons. So if you looked at the fraction of the 5, 6, or 7-sided polygons, what is the entropy or what is the disorder in the system? So for a perfectly ordered hexagonal system, of course P6 is 1, and the entropy turns out to be 0 for this because it's perfectly ordered. Now, the beetle, of course, these cells, I should remind you, are about 5 to 8 microns wide. Right? But the beetle's structure is curved. So what we were interested in finding out is what is the entropy for the system as you look at the curvature, even though the radius of curvature for the beetle is actually quite large in comparison to each individual cell, but we were quite interested in finding out if there is any dependence. So you can take an image like this, locate the centroids, and then you can convert that image into a Voronoi polygon, and all the white ones are the 6-sided, the 7-sided are the red ones, and the 5-sided are the blue ones. And so you can tell, if I were to take this image and look at it, the entropy is 0.96. I've calculated for this. So there are a fair number of 5-sided and 7-sided polygons for this. But you will also notice...
So is it Shannon entropy?
Huh?
Is it Shannon's entropy?
Yes. So the question then is that oftentimes you will find that these the 5-sided and 7-sided polygons more or less come together. And for any pattern forming system, if you were to have a Rayleigh-Benard instability, for example, you will have these penta-hepta defects. They always come together. And in this case, there are more number of 5-sided in comparison to the 7-sided, but often they come in pairs. So here is the poor beetle. Well, it's dead anyway. It was dead when we bought it. This one is a $5 beetle. So we got started with this because I bought this very rare red beetle, and I had bought it using my own dollars, right? So it was $500. It's about an inch long. And one of my students, Mattia Chernay, who now works for Procter & Gamble in Germany, he came to me and said, "Can I look at it under a microscope?" So I said, "Yeah, sure, go ahead, look at it. But please don't break it, bring it back." So in the evening he comes and says, "Oh, Mohan, I broke the thorax of the beetle." Right, so it's being beheaded. So we decided, well, we'll study this beetle anyway. So I still have the red beetle. I can't get myself to dissect it completely. It's $450, so. But this is a $5 beetle, and it lives in Texas. For those of you who are in the U.S., there's a reason why I say it lives in Texas, and it's $5 only. And it's a very political thing. So if you're not from the U.S., it's not a joke for you. So here is the beetle, and the most curved parts of the beetle, of course, is here, and you will see that as you increase and go to higher and higher curved parts, the entropy does increase. So this is not a surprise. But what is a surprise to us, and we've yet to figure this out, is the fact that each one of these cells is only 5 or 7 microns, but the radius of curvature is much bigger than that. But it still seems to have an impact on what the entropy is for this particular beetle. It's true for all the Chrysinia gloriosa beetles that we've looked at. We've looked at about 100 of these, and it's true for all 100 of them. Higher the curvature, the greater is the disorder, but that's not a big surprise. So here's a map of 17,000 cells, and there's a significant fraction of 5 or 7-sided polygons, and the entropy depends on the location where you look. So you can, people have talked about confocal microscopy already, but the only thing I want to tell you is the confocal microscope allows you the ability to look and build a 3-dimensional structure without actually dissecting the sample. So we did that, and here is an interesting image. So this is the top of the beetle exocuticle, and here is the bottom of the beetle exocuticle, so to speak. So we've gone from the top to here. And somewhere in the middle, what you can see is very nice, sort of a spiral organization of the fluorescent intensity. And so, as I said, this particular beetle is intrinsically fluorescent, so you Now it's not green fluorescence, the color is false color, but I forget the wavelength at which it's fluorescent. It's a 514 excitation, and we look at the fluorescence above 530, but the coloration here is false. But the essential idea is you have a polarization, a pattern of the intensity which sort of matches the pitch of the helix, if you will. So if I were to take the bright to the dark regions and measure it as a pitch, I would in fact get the right pitch for the green reflection. And I'll tell you in just a little bit why that's the case. So the question then is, what gives rise to this intensity pattern? There are probably two reasons why you can have an intensity variation. One, of course, is the fluorophore is inhomogeneously distributed in the Beetle exocuticle. There's no reason for me to believe that that would be the case. The other, of course, is a polarization-dependent fluorescence, which seems to be more likely. So if I have a helix, and Oleg Leventovich, of course, has demonstrated this, and so have we, that you can in fact get the information of what the optic axis is doing in a system by looking at the polarization of the fluorescence emission. So we take this to be a polarization-dependent intensity. So if the helical layers were winding around in sort of a spiral, and this is what you expect to see. And the spacing is quite consistent with what we think it should be for a green reflection. Right, so, and this is in fact a little bit exaggerated. This is the three-dimensional reconstruction of that. Each one of these cells seem to have a protrusion. Now, the protrusion is not as high as it appears on this because of the aberrations. We didn't match the refractive indices very well. But the point is, each one of them seem to be a little bit out of the plane, and that in fact is true. And what the Beetle, of course, the Beetle surface is really flat. If you use an AFM or an SEM, you can tell the Beetle surface is incredibly flat. Now the question then is, what are all these protrusions? The protrusions are in the Beetle exocuticle, and on top of the Beetle exocuticle, the Beetle secretes a wax layer to protect itself. And so the wax layer is, of course, really flat. But what's underneath, the chitin, is not flat. It is, in fact, protruding out of the surface. And so this is something Anderson Pace also observed in 1972. And just because it's published in Science doesn't mean you get lots of citations. This paper, when we looked at it, had one citation. It's an incredibly beautiful paper, but it has one citation. Now it has three. Two of those being my citation. Right, so Pete Vukusic and Sharon Jewell and Nick Roberts also looked at a slightly different beetle. And so here is the, again, a jewel beetle, looking at the confocal at various wavelengths, so they are much richer than we are. They have a 514 line, 543 line, 594, and a 633. I don't know what a 594 laser line looks like, but anyway. So we have a kryptonine that's 568. So, but at any rate, they looked at the confocal micrographs as well, and here it is in dark field, and they did a fair amount of analysis. And they came to the conclusion that the color of this results from two sets of helical pitches. Right? So one on top of the other. So there is the predominant green, and then there is the orange or the red. And so they modeled it based on, you have a pigment in the back of the beetle. For the light that's not reflected, much of it is absorbed by melanin. And so you have pitch number 1 and pitch number 2, and on top of it is wax. And so they sort of seem to think that this exocuticle has a double pitch. At least that's the conclusion they came to. I don't need to say anything about this, it's already been said a lot before. Okay, so if I had a cholesteric material, so I can have a right-handed helix or a left-handed helix, and the peak reflection is of course dependent on what the refractive index is and what the pitch is. And the full width half max is, of the reflectance peak is dependent on what the pitch and what the birefringences are. Now, so the question is, why will these patterns, so it's fairly well established in the late 1960s that the reflection is because of a cholesteric fluid or because of chitin being deposited as a cholesteric material. And the stuff that I showed you from Pete Vukusic and Sharon Jewell was that they considered this to have two sets of pitches. And what we were interested in is trying to figure out why these structures exist. And so we ran across Paweł Piranski's work on a synthetic cholesteric material. So this is also an incredibly beautiful paper, just as it is for all of Paweł's work. And so on the right-hand side are the images of a siloxane liquid crystal that Paweł studied. And what they found was at the free surface, so as you've already heard a number of times, the director for the liquid crystalline materials are very dependent on what the surfaces are. So most of the time at a glass surface or some surface, it's planar depending on what you have on the surface. And at the air liquid crystal interface, the director is usually perpendicular to that interface. So, and what Paweł noticed was that these were patterns, these are essentially defects that appear on the free surface of the cholesteric film. And so these are, so he modeled based on the energy calculations, he thinks that this is a focal conic defect that is on the surface of on the free surface of the cholesteric fluid, if the fluid has a free surface. And so these, of course, have protrusions on them, which is what we end up seeing in our confocal images as well. And the protrusion is not very large. It's on the order of maybe 0.3 microns from the flat surface. So the essential idea then is the helical axis is normal here, and these lines are supposed to be showing you the twisted planes. And then there is a defect, and so these patterns are then formed by defects on the free surface that are packing the surface. So in this particular case, this is the Beetle structure. So this is the confocal images showing the spirals, and here is the SEM. This is the wax layer, and you can tell that there is the helical pitch, and of course this is in the interior of the exocuticle, and so you see these spiraling layers at the top. So these are the defects that are packed on the surface of the liquid crystal. Now, what you will notice is if I have a defect like this, and the spacing, the cholesteric pitch is essentially the same here as it is here. But at that interface, it is almost as if I have to dilate the pitch. So very close to that defect, you will see it appears as if there are two different distances, or two pitches, as it were. And my contention is that in the work of Pete Vukusic and Roberts, they are essentially seeing this dilation and think that there is a double pitch, but that's still to be decided. Okay, so here is sort of the, if you had a free surface of a cholesteric fluid, these are the patterns that you will find. These are all focal conic defects that are organized on the surface of the cholesteric fluid. So I think what we have in our system, so this is again from Paweł Piranski's work. Here's the AFM that they did, and here's our model for what the helical axis is doing. Now the optics of this is quite cumbersome and complicated, and I'm not going to spend a whole lot of time talking about that for two reasons. One, I don't completely understand that, so I don't want to bore you with all the things that understand. And 2, I don't understand that. So here's a paper by Mehta, again using the same cholesteric fluid, and you prepare a very thin film by spin coating, and you bring it up to the temperature at which it is a cholesteric fluid, and what you will find is very quickly it reorganizes, and so here is the free surface forming all these defects. And so the patterns on the Beetle, we think, is largely driven by defects that are decorating the surface of the Beetle, simply because it has 2 different surfaces and the boundary conditions need to be satisfied. So you can sort of spend some time thinking about this, but again, anyway, because of the defects that you have, you essentially get a dilation of the pitch, and it almost appears as if you have 2 different sets of pitches, but you don't. One is being dilated simply because of geometrical constraints. Okay, so with that, selective reflection of circularly polarized light is largely because of the fact that chitin is deposited as a cholesteric phase, and then of course it's solidified, and the patterns are all there because of the defects of the focal conics on the surface of the Beetle. So with that, let me quit. So these are the partners in crime. So this is Vivek Sharma, Changok Park, Mattia Cherney. So in fact, Mattia is an interesting character. He is the one who started this work with us. He was working on polymer composites, and he got bored with working on polymer composites, so he started doing this work. And he did this for a good 1 year. Right? So now he has a job at Procter & Gamble. Those of you, if you want to have colored hair, he's making colored hairspray for you guys. Right? And so that's Shu Shaya, who was also involved in the work, and I don't know who that guy is. Exactly. That's why I don't know who he is. My acknowledgements to Helen Janadilla Suni and Nina Allen at North Carolina State, and of course, money for this came from National Science Foundation. And thank you for your attention.
Any questions?
So when you use a confocal microscope to see the cholesteric, usually it will cause some error because
Sure.
polarization of the light will follow if this material thing fall into the Mohan machine.
Correct.
So did you
Correct for it? No. We know it's there, but the emission. Remember, what we are doing is we are looking at very thin planes to put the image together. So when we look at the almost 200 nanometer thickness XY objects, we don't necessarily have to be very concerned with the rotation of the polarization, although we have to be. But the overall structure, of course, we're not making any quantitative statements about the state of polarization from the confocal microscopy, other than saying the spacing that we see because of the fluorescence is commensurate with the pitch of the helix. If we really want to understand what the polarization is, then we really have to spend time thinking about the optical rotation of the polarization. You are correct, and we are completely aware of that.
No questions? Right, let's thank Professor Srinivasarao again.